Hello and welcome to Samsplaining Science. I'm Sam, I'm your host. I'll be Samsplaining the science, and today we're talking about blue light glasses. Are they legitimate or are they just a load of barnacles? Sounds like a load of barnacles. Please get the SpongeBob reference. Anyway, before we get into that, let's not skip the pleasantries. Hello, how are you? How's the first week of your new year been? I hope it's been well. Mine's been going okay so far. Been keeping busy. We're on the second season. This is the first episode of the second season of the podcast, which is very exciting. I'm making some new updates, some changes for the show, little by little, incremental changes, as they say. I'm going to not do the intro music anymore, the royalty-free music. For the first season, if you listened, I don't know, it was just a pain in the butt, and I felt like, why am I doing this? There's no need. So I'm cutting it. Second season, no music. This is a musical-free podcast, unless I change my mind again at some point in the future. But for now, no music. One of many changes that will be implemented throughout the second season of this here show. But yeah, no, it's, first year of the new week. Have you heard? First week of the new year. Been keeping it busy, but I'm excited for things that will be happening throughout the year, and I hope you feel the same. It's been a long week. I can't believe it's only 7 days into the new year, but whatever. Maybe you're like me and you've already broken your resolution. My resolution was to post every episode on Friday. I'm recording this on Saturday at 11:30 in the morning. Amazing. So I absolutely nailed it. You probably did better than me. I hope you did better than me. I bet you did. I've got this creaky chair that I've been trying to edit out of my episodes, but now I'm just leaning into it, and it's going to be my co-host. Perfect. She says hello. Anyway, let's get into what this episode is about. That's enough pleasantries. Happy New Year. Hope your first week was good. Hope you're looking forward to the rest of the year. Now let's talk about some blue light glasses. The motivation for today's episode was really just that I wanted to know what the deal was with blue light glasses. A couple years ago for Christmas, my sister got me these, and I got her a pair. We actually bought each other a pair of blue light glasses. And I've used them occasionally when I remember to, because people say, oh, it's good. It helps regulate your sleep and all these things. And I'm like, how? What is this? So I wanted to learn about blue light. I wanted to learn about blue light blocking glasses. I was just curious to see, is this legit, or is it a placebo effect type thing? So that was the motivation for this podcast, is that I wear these blue light blocking glasses, and I don't really know if they're scientifically proven or if it's more just a fashion statement. Because I will say they were cheaper, because I also wear real glasses while I wear contacts, but these were a lot cheaper than buying frames from the eye doctor, So I will say that. But yeah, that's what the motivation for today's episode was that I just didn't know something. And I was like, I want to know this. And that's a fun way to live life, is to acknowledge the things that you don't know and then search for an answer from reliable, credible sources. Wonderful. Okay. So, like I said, this episode we're talking about blue light glasses. Hopefully by the end of the episode, we'll have a better idea as to whether these blue light glasses are legitimate, if they actually help us in some way, shape, or form, or if they're a waste of money and plastic. Okay. This episode is sponsored by blue light glasses, imagine? No. Anyway, with that, let's get into today's questions for the episode. So we have 2 questions today. The first one is, what is blue light? What does that mean? We're going to talk about what blue light is and why we would want to block it out in the first place. And the second one is, do my blue light glasses work? We'll go through 2 recent studies that look at the effectiveness. Efficacy? Effectiveness? Effectiveness is a word, right? It is. I'm declaring it a word. It's my word. 2 recent studies that look at the efficacy of blue light glasses. Okay. So question 1, what is blue light? To answer this question, we're going to revisit our old friend, the electromagnetic spectrum. Here we can look at electromagnetic radiation based off of its wave properties. So specifically looking at wavelength, and wavelength tells us the frequency of the wave and the energy of a wave particle. So in the electromagnetic spectrum, we have a wide range of wave particles, ranging from radio waves, which have a very long wavelength and very low energy, to gamma rays, which have a very short wavelength and a very high energy. So if you've noticed, it's kind of like swapped. So when a wave has a very long wavelength, its energy is low, versus if it has a very low wavelength, it has a very high energy. It's kind of mismatched like that. On the electromagnetic spectrum, or the spectrum of electromagnetic radiation, there's a small portion of that in which this energy is visible to the human eye, and we call this visible light. And in this section of the electromagnetic spectrum, it looks like a rainbow, where we can see red, orange, yellow, green, blue, indigo, violet wavelengths. Within the visible spectrum, we have red colors on one side and purple, blue on another, where the red side has longer wavelengths. So the wavelengths of things that we perceive as red have a longer wavelength of about 700 nanometers, whereas the things that we perceive as blue have wavelengths of about 400 nanometers. So red light has longer wavelengths and less energy, whereas blue light has shorter wavelengths and more energy. So kind of putting this in perspective, like when we see light energy reflecting off of surfaces or bouncing off of surfaces, if we see a red wall, we have radiation that is reflecting off of that red wall and reflecting back to us at around 700 nanometers wavelength. Likewise, if we see like a blue ball, it's the same thing. So what we see, the colors that we see, depend on the wave properties of the radiation and the reflection of light. But it's important to note that this part of the spectrum is visible light, so it's everything that we can see. Because other sides of the spectrum, like radio waves, we can't see radio waves, even though they're used to, transmit signals for radio and TV and stuff. And we also can't see x-rays. So if you've ever broken a bone or something and you've gone to get an x-ray, when they give you an x-ray, you can't see the x-rays shooting through your arm or your leg or whatever. Those aren't visible to us. Whereas the visible portion of the spectrum, we can see the light rays because that's what our eyes are allowed to pick up, because that's just the way it is. Another thing that I did want to mention before we move on is that we can see multiple wavelengths at once to get like a combination of colors. So like white light, for example, is a combination of every color of visible light. Whereas if we see nothing, if we see darkness, there's no visible light being reflected or emitted. So when we see white light from our phone screen, for example, for texting somebody, and we see white light in the background, that's a combination of like red wavelengths, green wavelengths, blue wavelengths, etc. So that was kind of a brief, I kind of rambled a little. We won't worry about it. That was kind of a brief overview of the electromagnetic spectrum. But as you know, this episode is about blue light. So we're really going to be focusing on this very small portion of the visible light spectrum, which is a small portion of the electromagnetic spectrum. But maybe you're wondering why blue light? Like, why are we focusing on blue light and not red light? Well, remember that blue light has higher energy, shorter wavelength, higher energy. And in recent years, blue light has been suggested to play a role in sleep cycles and specifically affecting the circadian rhythm, which is our 24-hour internal clock that tells us when to go to sleep and when to wake up, when to get sleepy and when to be alert and awake, based on like a 24-hour cycle. And recent research has suggested that exposure to blue light can impact this 24-hour cycle. So this review article by Siegfried Wall and colleagues, it was published in 2019 in the Journal of Biophotonics. It's linked below if you want to take a look. This review article summarized it really well. So I'm going to pull some figures from this article to try to samsplain it all, to try to explain why blue light, what is blue light, and how it could potentially be impacting our circadian rhythm. First, let's start out with the circadian rhythm. The biggest, I don't know if it's the biggest, one of the biggest contributors to our sleep-wake cycle is a hormone called melatonin. You might have heard of melatonin. Some people take melatonin supplements to go to sleep at night. Basically, melatonin, when melatonin is high in our bodies, when the level is high, we get drowsy and we go to sleep. And then when we wake up, after we are well rested, melatonin should be low. And then throughout the day, the level should be relatively low until the sun sets. And then it starts to increase little by little until we get to a point where it's time to go to bed. And it increases throughout the night until it peaks around the middle of the night. And then it reduces until we can wake up. So the level of melatonin is what is impacting our sleep-wake cycle, specifically in a 24-hour period, right, where we are awake and alert during the day, and then the sun sets and melatonin starts getting released. Melatonin makes us tired. We go to sleep. As we're sleeping, the amount of melatonin in our system peaks and then goes down. And then as we wake up, the melatonin level is low. And then it's low throughout the day, and then it cycles again, so that it's low throughout the day, and then once the sun sets, the cycle repeats. You might be asking, how does blue light affect this? That's an excellent question. Let me tell you what I learned about this. So because the melatonin in our system is kind of dependent on sunlight, right? Like melatonin starts to increase when the sun goes down, and then when the sun is up, melatonin is low. Because of that, you can probably guess that light has something to do with melatonin. Exposure to light, whether it's sunlight or brightness or whatever, can impact the release of melatonin. So, as you may be aware, our eyes, our eyeballs, collect light rays from our environment, whether we're indoors, whether we're outdoors. Light, whether it's artificial or sunlight or whatever, comes into our eyeballs, and at the very back of our eyeballs, so like closer to our brain, there are certain cells in an area called the retina. You might have heard of the retina of your eye. So the retina have these specialized cells called retinal ganglion cells, and these cells receive light waves. They're called photoreceptors, so they receive light, photo, and they send the visual stimuli to the brain. So there are different types of cells in the retina, one of which is the retinal ganglion cell, but then there's also cells called rods and cones, where rods are responsible for detecting light and dark, or rather like black and white sort of patterns. And then the cones are responsible for detecting color. So all of these cells, the retinal ganglion cells, the rods, the cones, they all have the ability to detect light and send that visual stimuli to the brain. We're going to get a little more specific, dive a little bit deeper. but not too much, I promise. So retinal ganglial cells, some retinal ganglion cells contain a protein called melanopsin. Melanopsin is what makes some of these retinal ganglion cells photosensitive. So these are the intrinsically photosensitive retinal ganglion cells, or the IPRGC. Basically, melanopsin is a protein that can absorb light. And melanopsin containing cells then send signals to a part of the brain called the suprachiasmatic nucleus, or the SCN. And this region of the brain, which is kind of like right behind your eyes, really, it's a part of the brain that's known as the master clock of the brain. So it helps to regulate the circadian rhythm. And it's part of a pathway that leads to, eventually, the pineal gland. The pineal gland is responsible for secreting melatonin. Remember, melatonin is the hormone that makes us tired, right? So indirectly, these light-receiving cells are connected to melatonin. And this pathway is kind of like a negative feedback pathway in a way, where when these cells are receiving a lot of light, and the melanopsin is taking in a lot of light, receiving a lot of light, and sending a lot of nerve signals to the brain, then that pathway is turning off the function of the pineal gland. And when the pineal gland is turned off, it is not releasing melatonin, which during the day is great. When we're outside and we have a lot of sunlight, we don't want to get tired, right? We want to be awake. So when we're exposed to a lot of light, we don't want a lot of melatonin. It's bad if we're exposed to a lot of light at a point when we're trying to go to sleep. And this might be relevant for shift workers, for night shift workers, for example. So if you or someone you know is a night shift worker, you might have blackout curtains, right? Where if you have to sleep during the day, you need to limit the amount of light that's getting into your eyes so that your brain can produce melatonin to make you sleepy. Because if the light is there, the melatonin is not being released. So all of that to say, a quick summary. During the day, the light is collected in our eyes, and that sends signals that suppress the function of the pineal gland, so the pineal gland does not release melatonin. But then at nighttime, when theoretically there's less light, the pineal gland is no longer suppressed, and it can do its job and release the melatonin, which makes us sleepy and want to go to bed. But it's actually important to note that this isn't about light in general, right? We're talking about blue light. So why do we care about blue light in particular? So this graph that I'm showing, if you're watching on YouTube, youtube.com/@samsplainingsci, I'm showing a graph from the review paper that I've cited where we are looking at a spectrum across many wavelengths of a few different curves. So the plot is showing signals and responses across different wavelengths on the visual spectrum on the x-axis. And then I'm just going to kind of describe what each line means because it's a little overwhelming when you're first looking at it because there's a lot going on. If you're following along in the paper, this is figure 4 of the Wall and colleagues review paper in 2019. So figure 4, there are dotted lines that show the light absorbance for a given wavelength for different cell types in the eye. So as I mentioned, we have rods and cones, where rods help us see light and dark, black and white, and shades of gray. And then the cones help us see colors like red, green, and blue. So red cones have a higher absorbance of light. They take in light at higher wavelengths, which are the red side of the spectrum. And then the green cones take in photons of light in the green spectrum, and then the blue take in photons of light at the 430-ish nanometer end of the spectrum, or blue light. And then the rods are more central. They're sort of like in the middle. They take in just like general light. So those are the dotted lines on the curve. Now let's look at the solid lines. So for the solid lines, we have spectra for other conditions that aren't necessarily talking about absorbing the light. So we'll start with the blue curve. So the blue curve is the blue light hazard spectrum, which is basically the blue light that is detectable by the human eye. It peaks at around 440 nanometers, so that's like the highest point of the curve. But it really ranges from like about 380 nanometers to about 540. So technically, I guess it could cover like parts of the violet and indigo spectrum, and then also cover parts of the green spectrum, because technically there is blue and green, you know, like when you're mixing colors. Remember like in kindergarten when you would like mix yellow and blue and get green? For some reason, I think, was there like a Barney episode about that? Because I'm thinking about it now and I'm immediately thinking Barney. Did you see there's a documentary about Barney now? They're like, apparently, when I was a kid, I had no idea any of this was going on, but apparently people were sending Barney death threats. Like, I'm just trying to learn my ABCs, dog. Anyway, I will be watching that because, I don't know, just because I like to waste time is what I like to do. And I like to waste time on things that are not, like people are like, oh my God, watch this show, watch White Lotus. No, I'm going to watch a Barney documentary instead. Why? I don't know. That's just how my brain works. Anyway, the blue solid line is the blue light hazard spectrum, which is the blue light that our eyes can detect and that our eyes respond to. Next, we'll look at the green line. So the green line is the melanopsin response line. So remember, melanopsin is that protein in our retinal ganglion cells that help detect light and send signals to the brain that, hey, it's light out. There's light, general light, not necessarily a certain color or a certain, shape or anything. It's not about vision. It's just about like brightness, essentially. So the melanopsin line overlaps a little bit with the blue light hazard line for a decent amount. Actually, more than half, I think, of the melanopsin line is overlapping with the blue light line. And that, I guess, is showing that the wavelengths that elicit the signals in our retinal ganglion cells are the same wavelengths that are in the blue light hazard, meaning that the blue light can impact melanopsin. And then the last solid line that I want to talk about is the smartphone spectrum line. So this is the light that is emitted from our phones when our phones are at full brightness. And this curve has 3 peaks. One at the bluish side of the spectrum at around 450 nanometers. Another peak at around the greenish spectrum at around 540 nanometers. And then one closer to the reddish side of the spectrum at around 600, 620 nanometers. The highest of these 3 peaks, the most intense, is the blue peak at 450 nanometers. It's the sharpest peak, but it's the tallest. It's the most intense. And it also falls directly under that blue light hazard line. So essentially, the phone irradiation, like the lightness, the brightness from the phone, and the blue light that our eyes can detect, and the light that activates the melanopsin in our eyes, all kind of overlap, which is basically showing that, okay, blue light, specifically blue light from our phone, can activate our melanopsin in our retinal ganglion cells, and that starts the pathway that eventually ends up at the pineal gland to say, stop releasing melatonin. We don't need it right now because it's bright. We don't need to sleep because there's light coming in. And when it's dark, then you can start releasing melatonin, but as long as I'm sensing light, you don't need to release melatonin. That's what I'm taking away from this. I know it's complicated, but I think that is the brief summary of this slide. But I guess the takeaway that I just outlined can be a big problem, right? Especially if we're on our phones late at night when we're supposed to be getting ready for bed. If we're looking and we're getting all of this light into our eyes and our melanopsin is firing away to our pineal gland to not release melatonin, so we won't get tired because we're stimulating our eyes with light. So one way to potentially fix this problem, instead of putting down the phone, because let's be real, who wants to do that? not me. So instead of putting down the phone, let's instead block the blue light from our eyes. Let's find a way to filter the phone light so that we're only really looking at maybe the green and the red peaks, because the blue peak is the one that really overlaps with the melanopsin. If we look at just red light, maybe the melanopsin won't be as active and that pathway won't be as active, so that the pineal gland will be able to release melatonin even if we are looking at light things when we're supposed to be going to bed. This is the whole theory behind blue light blocking glasses. So that's sort of like the logic. It makes sense to me. I really hope that my explaining it makes sense also, because I really see the theory as to like why blue light blocking glasses can help with regulating the circadian rhythm and helping with regular sleep-wake cycle. I understand that now based on this sort of analysis of light spectrum and how the light spectrum relates to the parts of our brain that tell us when to go to sleep. But let's see if that theory can carry through into practice. And when we look at studies of blue light glasses, if we look at blue light glasses in a scientific experiment to see, does this really work? Does using blue light glasses actually help moderate our sleep schedules? So in order to address that question, we're going to look at two studies, one of which is looking at sleep health. This is a study by Dr. Baigalk, sorry for mispronunciation, and colleagues. It was published in 2021 in the journal Sleep Health. And this was a randomized control trial that tried to see if blue light glasses helped improve the sleep patterns and the sleep quality of healthy controls. So let's talk about their experimental design. So they had 20 participants in this study. The average age was about 32 years old. There were 11 males and 9 females. And they had a random assignment of blue light blocking glasses versus control, where essentially the study lasted 3 weeks. The first week was no glasses at all. The second week, they were randomly assigned either blue light glasses or glasses with no filter on them. #NoFilter. And then the third week, they swapped. So if they got blue light glasses in week 2, they would get clear glasses in week 3. And if they got clear glasses in week 2, they would get blue light glasses in week 3. And each day of those weeks 1, 2, and 3, they measured sleep subjectively. So each day the participants would keep a sleep diary and say, here's how I slept. And they would note like, okay, I tried to fall asleep at this time. Maybe I tossed and turned for a little bit or whatever. They would just keep like subjective analysis of their sleep. I woke up at this time, whatever. So that was like the subjective sleep measures. But they also took objective sleep measures based on wrist actigraphy. I don't know. But this was basically like a sleep tracker on your wrist that tracks light, movement. It can be used to study sleep quality, from my understanding. So they specifically, with these measures, looked at sleep onset, number of awakenings, and total sleep time. And they got those 3 measures both subjectively with the sleep diary and objectively with the tracking of the wrist. So that's sort of their method and their experimental design. But if we get into the results, they actually found that when they compared the control glasses to the blue light glasses, that the blue light glasses in the subjective measures of saying, here's how I feel, what I wrote in my sleep diary, those subjective measures were reduced in people who use blue light glasses versus controls, versus the clear glasses, I should say. Specifically for the sleep onset time and the number of awakenings. So when people wore the blue light glasses, they said that they had shorter sleep onset time In other words, they laid in bed for a shorter amount of time before falling asleep, and they reported less awakenings in the middle of the night based on their subjective analysis. The change in total sleep time did not change for subjective analysis. When we look at the objective measure, so this was the measure that came from the risk tracker, they actually found that there was no difference whether people used the blue light blocking glasses or the clear glasses, the control glasses. So for the objective measures, total sleep time, sleep onset latency period, and the number of awakenings was not statistically different between the blue light blocking and the clear glasses. It's important to note that in the paper, the authors mentioned that they didn't completely blind the participants, or they didn't keep the participants from knowing which glasses were which. Because blue light glasses, it's kind of obvious when you have blue light glasses versus when they're just like clear. I don't know if you've ever had blue light glasses, but like sometimes they have like I'm showing it in the video now, but they have like a reflection that looks kind of bluish. Because essentially how they work is the blue light is hitting the lens and the blue light is being reflected back out, and only the higher wavelength light is passing through the lens. So the lower wavelength light, so like the blue light at around like 400 nanometers, is being blocked by the lens and being reflected back. And then the only wavelengths that are passing through are higher wavelengths, like 500, 600, 700 nanometer wavelength, or like green, red light. Okay. But it's kind of obvious. The point that I'm trying to say is it's kind of obvious when you have blue light glasses, because the reflection, you can kind of tell that it has like this like bluish tint. So they noted that the participants probably knew that they were using blue light glasses, and when they know that, this is the experiment, like this is the experimental group, they have somewhat of a bias. So in their subjective measures, they might have said, I woke up less when I wore my blue light glasses, but they actually didn't when we look at it objectively with the risk measures. I don't know, I think that's kind of a good point that they made, and I'm glad that they mentioned it in the paper, because it's always kind of, you like to have a reason when the subjective and the objective measures don't match up, because you're like, where did the bias come from? If we're looking objectively, theoretically, there should be less bias. So like the subjective measures, like how did they know to bias the experimental group? And it's because it was like kind of obvious that they had blue light glasses. But anyway, the conclusion of this study is that the blue light blocking glasses didn't significantly improve the objective measures of sleep time. So in other words, the blue light glasses really did nothing. It didn't change the sleep quality for these participants. Before we move on to the next one, I just want to talk about some limitations from this study. One, of course, as I always complain about, the sample size. This was a study in 20 people, which is pretty small, but also the sample was healthy. These are people who did not have insomnia or did not struggle with like any really sleep disorder of any kind. They were otherwise healthy. So, maybe the difference would be bigger in a population that have a sleep disorder like insomnia. And actually in the discussion, the authors cited a study from 2018 that showed that blue light blocking glasses increased total sleep time in 15 people who had insomnia. So there's some evidence out there that these can help regulate sleep for people who struggle with sleep disorders like insomnia. But as far as like the regular Joe Schmo like me, probably won't change my sleep patterns that much. Overall, though, the data from this current study, and honestly the general consensus that I found in the papers that I looked through and the abstracts that I read through, the data is not strong enough to reach significance in an otherwise healthy population. So like it's hard to say that the blue light glasses make a significant difference, let alone a big difference in sleep quality in people. So that was kind of the takeaway from this, was sort of like, maybe, I don't know, maybe it's sort of like a placebo effect, right? If you know you have blue light blocking glasses, maybe you'll convince yourself that you woke up less during the night and you went to sleep faster, but objectively, probably not. Yeah, I agree. My co-host is really putting her 2 cents in today. Okay, so that's blue light blocking glasses and sleep. But another thing that I was curious about, that I didn't really talk about the science behind, but I was curious because a lot of people say, oh, blue light blocking glasses are great for eye strain. And like my job, I look at a computer literally all day long. I do coding, I do image analysis, so I'm constantly looking at screens. And if I'm not working, if like I'm at home, I'm online. I'm chronically online scrolling. So like I'm looking at a screen, as long as my eyes are open, I'm looking at a screen, to be honest with you. So I was like, oh, you know what? Like eye strain, maybe like my blue light glasses will help me with my eye strain and protect my eyes from me looking at screens 25 hours a day, 8 days a week. So the second study that I wanted to look at is a research article called "Do Blue Light Blocking Lenses Reduce Eye Strain from Extended Screen Time?" A double masked randomized control trial. So this study was from Australia. I won't try to do an Australian accent though, I promise. You might ask, you might be, Sam, please give me an Australian accent. I'll say, no. Okay. I'm sorry. I'm not. Okay, the first author of this article is Sumeer Singh and colleagues. They, as the title suggests, they were interested in looking at blue light glasses and eye strain. And not necessarily caring about sleep or circadian rhythm, but thinking about if blue light exposure, especially like looking at screens for long periods of time without a break, is tied to eye strain, and whether blue light, blocking that blue light, can reduce the level of eye strain. So here the authors tried to see if blue light blocking glasses can help with eye strain of computer users. So in this study, there were 120 participants that were all in their 20s. Each of the participants were symptomatic for computer vision syndrome, or CVS. And symptoms of computer vision syndrome include dry eye, blurred vision, redness, and headache. And reading this, I now have diagnosed myself with CVS. So now I'm trying to see, are blue light glasses going to solve my problems? Because now I personally relate to this cohort of participants. They are me, and I am them. We are one. So the researchers took these 120 participants, and they were a double-masked, double-blinded study where participants were split in half, first into positive and negative advocacy groups. And this was actually an interesting way to control for like the placebo effect, I guess. They were briefed on the objectives of the study in either a positive light or a negative light. So they were basically briefed on the study to say, here's how it's going to work. You're going to take these glasses and wear them and, go on the computer or whatever. But the tone with which they were told these glasses was either positive or negative. It's like, oh, you're going to take these really cool glasses and go on the computer and see if they help. Or they're like, oh, you're going to take these dumb idiot glasses and go on the computer and see if they change your eyesight or whatever. So there was like a positive and a negative advocacy group. And then so there was like 60 in each group. And then within those 60 positive and 60 negative, they were further split up into two to either get the blue light blocking lenses or to get control lenses, which are just, they don't have the blue light blocking. But they were coated with a UV coating. So they did maybe have a little bit of like reflectiveness, like I talked about, but they did not block the blue light from passing through the lens like blue light blocking glasses would, as the name suggests. So each group was divided, and then they were assigned their blue light blocking glasses, but they didn't know which one that they got. It was either blue light blocking or control. And then they did Then they took measures before the task. So they took pre-task measures of eye strain questionnaire. They measured their eye movements. They measured near point of convergence, which I think is like when you go to the doctor and the doctor like is like, follow my finger, and you like go cross-eyed because you're like trying to follow their finger, you know? I think that's like an eye measurement thing. So that's what they did. So they took all these measurements before the task, and then they sat down on the computer for 2 hours wearing the lenses that they were assigned. And then they also measured during the task while they were on the computer, they measured their blinks. And then after the task ended, after the 2 hours on the computer, they took those measurements again. So the eye strain measurements, the movements, measurements, and so on after the task ended. So to get into the results, they first looked at the SSQ, which is the Subjective Symptom Questionnaire, SSQ, across the 4 groups. So the positive and the negative, and then within the positive and the negative, they had a control group, and then they had a BBL group, which means something very different. Maybe down under, BBL means blue blocking lenses, but where I come from, BBL means something very different. But I digress. Essentially what they found is that across groups, the change in the subjective symptom questionnaire before and after the computer task was not different across groups. So in other words, their reported measurements of eye strain, and they're saying, oh, my eyes hurt, or like whatever, their self-reported symptoms changed to the same degree, whether they had the blue light blocking glasses or whether they had control glasses, and whether they were in the positive or negative leg of the study. They also found that there were no differences in any of the other eye measurements, including eye movement, including blink measurement, including the near point of convergence. All of these eye measurements across the groups were pretty much the same, in that there was barely any change. On average, there was barely any change before and after for each of the groups. There was a decent amount of variability, though. I will say that if you're looking on, if you're looking at the graphs, or if you're following along on the paper, I'm looking at figure 3 right now. It has like all of the measurements and then the change on the y-axis. There's like a decent amount of variability. So like you can see the box and whisker plots. The whiskers are like the things that stick out from the box, and they indicate the, like essentially the range of the data. And you can see that some groups have more variability than others. Like some groups don't really have much variability at all, whereas some have a lot of, like a very large range. But you'll see that no one group is that different from the next overall when we're looking on average. And statistically, there were no differences between each of the groups. So the conclusion that we can take away from this is that blue light blocking lenses did not really significantly change eye strain symptoms or eye measures in people who experience eye strain from computer use. And in the discussion, the authors also cite another randomized control trial that looked at blue light blocking glasses in eye strain, and they found that in CVS, in computer vision syndrome, they also found negative findings. So the blue light blocking lenses did not help the symptoms of CVS. In science, there's really strength in numbers. So like the more studies that are done on a certain topic, the more believable, I guess, the conclusion is when all of the conclusions agree. So that was just basically saying they found negative findings for this, and previous randomized control trials have also found negative findings for this. So the consensus is that the blue light blocking glasses don't really help with eye strain either. Which, like, okay, perfect. So I literally have these for no reason. Amazing. Love that for me. Okay. So that's the end of question 2. Do my blue light glasses work? No. No, they don't. I mean, it might affect people differently, right? We saw with the sleep study how it didn't really affect people who did not have sleep disorders, but maybe it could benefit people who have insomnia. So maybe it helps some people, but the data suggests that it's pretty unlikely that blue light blocking glasses can actually help with like healthy sleep patterns and with eye strain, or I should say, nor with eye strain. If we're getting technical with our verbiage. But anyway, do my blue light glasses work? Not for me, probably. Whoops. I guess I'm just a product of consumer America. What are you going to do? Anyway, the takeaways from this episode. First one is, I don't know, LOL. We need more studies to be sure that blue light glasses actually work. The general consensus right now is that they don't. They don't really help with sleep, particularly in people who do not have sleep disorders, and they don't really help with eye strain either, which are the two big reasons that I hear people say you need to use blue light glasses. So the science is really not in the favor of blue light glasses, especially if you're otherwise healthy. So what are you going to do? That's kind of a bummer. But you know what? That's part of life, right? Sometimes things don't go the way you expect them to. And just because something negative results doesn't mean that it's not worth sharing. Negative results are still worth publishing, even though big science might not agree. Only the most flashy experiments get published, but experiments with negative findings should get published too, and they should get attention. Even if it's not in our favor, even if I want to wear these so bad, even if I want to spend money on new frames without paying for prescription lenses, that's fine. I did it, and you know what? I might do it again too, because these were pretty cheap, and they're stylish, and they're cute. And that's one thing that I didn't mention, but I should point out, it didn't make anything worse, right? It didn't harm your eyesight. It just didn't change it at all. So it's like, if you want to wear it just as a fashion accessory, go wild. I'm gonna do that. I'm gonna wear these as a fashion accessory, because, you know, especially if you wear glasses like I do, when you go and you pick out lenses every year or like a couple years, I haven't bought lenses in a while, but or frames, I should say. When you go and you pick out new frames, it's always such a stress of like, oh my God, what am I gonna choose? What am I gonna choose? But now with these, like, you can choose one for like your regular glasses, and then you can have like cute alternatives with your blue light glasses. Just know that when you wear them, it's solely as an accessory. It's solely cosmetic while you're doing this. It will not, it probably won't help your sleep cycle unless you have insomnia. And it probably won't help your eye strain either. That's all. That's the little nuance for today. Fashion accessory, 10 out of 10. Helping with eye strain, maybe a 2 out of 10. The data's not really there, but it could be. Maybe we need more studies to see, but odds are probably not. Okay, I've rambled enough now. That's all for this week. Please don't forget to follow, rate, and review the podcast wherever you're listening, and subscribe on YouTube, please. You can also follow the show on Twitter, Instagram, and TikTok at samsplainingsci, so connect with me there and ask questions if you'd like. You can also submit your questions to samsplainingscience.com/ask, so if you have anything that you want me to samsplain, ask away. Thank you so much for listening to this week's episode. I hope you learned a little bit and laughed a little bit, and I will talk to you next time. Bye.